Now just to be handy a little, let me just start with the last reaction of oxymercuration, demercuration. Now, suppose this is the reagent, and looking at the reagent you have to identify this is oxymercuration, demercuration reaction, and once after identifying this is oxymercuration, demercuration, you have to know how to write the product. Now that mechanism you have to see once to understand, to get a feel why we are writing the product the way we are writing, and then ultimately you have to know how to write directly the product for that particular reaction. Now for this reaction we have learned that we will do Markovnikov addition without rearrangement. That means among the carbon who are making the pi bond, we have to choose the carbon which is more substituted and put a OH there. On the other carbon put a hydrogen. So put a OH here, put a hydrogen here. Now this hydrogen, remember, is coming not from water or not from other species. This is coming from NaBH4 in the form of hydride, which is clear when we have seen the mechanism. Now suppose you have, in order to understand it properly, now this hydrogen is coming from sodium borohydride. Fine. So instead of hydrogen, if I take deuterium, if I take isotope of hydrogen, then instead of H here there would be D. Suppose if I take D2O, then there will be no deuterium attached to the product, because hydrogen is not coming from water. From water you are getting OD. So if you take D2O instead of H2O, you will have OD here. But if you take NaBH4, there will be hydrogen here. If you take NaBD4, then there will be a D here. So this you have to keep in mind, that hydrogen is coming from sodium borohydride. Similarly, in this case, if you take the same reagent, now out of these two carbon, you have to choose the one which is less substituted. As such, both are 2-degree carbons. And but remember the reason why we chose 2-degree carbon, because of mercuric acetate getting hindered on a more substituted carbon. So we choose less substituted carbon to be attached, mercuric acetate to go on a less substituted carbon, and that's the reason why OH comes on a more substituted carbon. Now in this case, because of hindrance, suppose this is 1 and this is 2, because of hindrance, mercuric acetate will go on 1, because on 2 you will have a hindrance with this methyl group. So mercuric acetate will go on 1 and OH will go on 2. So here the level of substitution is same, both are 2-degree, both are equally substituted, but to be more specific, OH goes on a carbon which has more hindrance, so that mercuric acetate goes on the carbon which has less hindrance. So in this case 2 has more hindrance, so carbon number 2 will have OH, carbon number 1 will have H. This will be the major product. In this case, again, if this is 1 and this is 2, C2 has more hindrance because of this bulky group. C1 do not have this hindrance. So mercuric acetate will go on C1 and OH group will come on C2. So to get the major product, add OH group to more hindered carbon and add a hydrogen on less hindered carbon. So this is how you would write the product of hydroboration oxidation. Right? If we take the same substrate and we carry on hydroboration oxidation this time. If we take B2H6 first and then we take hydrogen peroxide in our basic medium. Now this time this is anti-Markovnikov addition without rearrangement. That is, OH will go on the carbon which is least substituted or which has less hindrance. So this is pretty handy, simple, easy, trivial. You get a OH here, you get a H here. You get hydrogen as per anti-Markovnikov rule, and you add OH to less substituted, less hindered carbon. This is how you write the product for hydroboration oxidation. Simple, easy. Now these two reactions are over. Now let's move to another kind of addition reaction. Now this addition is called Halohydrin addition. Now suppose I have a alkene. Suppose I have propene. Now on propene, do you remember how we did addition of bromine or chlorine for that matter? Now this CCl4 is solvent. In this case, what happened? You took a bromine. One of the bromine molecule, because of the presence of the alkene, developed a positive charge polarity. Other one develops negative charge polarity. The one developing positive charge polarity go and ask for electron. This forms a bond with one of the carbon. This comes out as Br minus. This forms a cyclic brominium ion. This comes, attack, breaks that ring, get attached to another carbon, form vicinal dibromide. This we have seen already. Now instead of CCl4, if I take water, then how the story will go? This time we have an alkene. Bromine is as such non-polar. Apart from bromine, we have water. Water is electron rich. We already know alkene is electron rich. These two won't react. Both are electron rich. No reaction. Bromine can react because in the field of alkene, one of the bromine will develop plus charge polarity, another bromine will develop negative charge polarity. The one having plus charge polarity will go and ask for electron. Electron would come. This bond will be formed. This will come out. Now this is same as the reaction of halogenation. So I have done it quickly. Now, in the last reaction, the story went like this. This bromide ion that has come out and the plus charge develop on this carbon, this will go and attack that C+. That's how we did it. Because last time we didn't have water. We had CCl4 and CCl4 will show no reaction. But we understand when this bromide ion comes out, it is under the cage of solvent. Solvent has surrounded this bromide ion from all sides, forming a bigger ball, a bigger ion than bromide ion. So the mobility decreases, the effective size of the ion increases. So that bromide ion, because it is shackled by the molecules of solvent, comes slowly, gradually, very slowly, and starts pouring its electron into the empty orbital of C+. So the reaction is slow. Now all around this molecule, you have water. Water here, water there, water everywhere. Now before this bromide ion that has come out can come gradually and start pouring its electron, water is already there. Now water will attack, not bromide ion. Now water will attack, form a bond, develop a plus charge, remove a hydrogen, and get rid of plus charge. So OH will get attached to this carbon. So you have halogen on one carbon and this hydroxy group on another carbon. So this is halohydrin. So what we would get is OH group on the carbon, which can have more stability of plus charge. We can form a more stable carbocation. That means OH will be on more substituted carbon and halogen on less substituted carbon. This is halohydrin addition. Nothing new, simple, easy.